Imagine traveling beyond every star you have ever seen, past the planets of our solar system, past the Milky Way, past the most distant galaxies visible to our telescopes, and then continuing farther toward a place where the universe itself begins to disappear. For most of human history, the universe seemed endless. But modern astronomy has revealed something far stranger. There is a limit to what we can observe, a cosmic horizon beyond which light has not had enough time to reach us. Beyond that boundary may lie more galaxies, more matter, and perhaps regions of reality that will remain hidden from humanity forever. Tonight, on What If Beyond, we will begin a journey across the largest distances imaginable. We will leave Earth behind, travel beyond the solar system, cross the Milky Way, move through the vast darkness between galaxies, and approach the edge of the observable universe. But what happens after that? Does space continue forever? Could there be other universes beyond our own? And is it possible that the true universe is far larger and stranger than anything we can ever see? Before we continue, tell me in the comments, what time is it where you are right now, and from which city are you listening? And if you enjoy calm documentaries about deep space and the mysteries of existence, consider subscribing to What If Beyond. Now, dim the lights, get comfortable, and let us begin a journey beyond the universe. Every journey into the universe begins from a place that seems ordinary only because we have never known anything else. Earth, a small world covered in oceans, clouds, continents, forests, deserts, and cities. From the ground, it feels enormous. A person can spend an entire lifetime exploring only a small part of its surface. Mountains rise beyond the horizon. Oceans stretch farther than the eye can see. Storms move across continents. The planet feels complete, self-contained, and almost endless. But seen from space, Earth changes. The atmosphere becomes a thin blue line. The oceans become patches of reflected light. The continents shrink into familiar shapes, surrounded by darkness. The entire history of humanity becomes confined to one fragile sphere floating in a vast emptiness. Every language ever spoken, every city ever built, every war, every discovery, every person who has ever looked at the night sky and wondered what lies beyond it. All of it happened here. And if we are going to imagine traveling beyond the universe, this is where we must begin. At first, our departure would seem familiar. A spacecraft rises above the atmosphere. The blue sky darkens. The curvature of Earth becomes visible. Cloud systems stretch across oceans like white spirals. For a moment, our planet still fills the view. Then the engines continue. Earth begins to shrink. The bright surface becomes a globe. The globe becomes a distant world, and eventually, Earth becomes only one object among many. The moon would be our first companion. It appears close from the surface of Earth, but the distance between the two worlds is already large enough to contain every other planet in the solar system if they were placed side by side. The moon is not simply floating above us. It is traveling around Earth across hundreds of thousands of kilometers of space. A spacecraft moving there still requires days. Radio signals travel quickly, but even they do not arrive instantly. The moon is our nearest cosmic neighbor, yet it already introduces the true scale of the journey ahead. As we pass it, Earth and the moon begin to look like a small two-world system. One blue and alive, the other grey, silent and airless. Behind them lies the sun. Ahead lies the rest of the solar system. The planets are often shown close together in diagrams, a neat line of colorful spheres surrounding a bright star. These images help us remember their order, but they completely hide the distances. The solar system is mostly emptiness. Mercury, Venus, Earth, and Mars occupy the inner region, but even these worlds are separated by tens or hundreds of millions of kilometers. The farther we travel, the more the emptiness grows. Mars may seem like the first realistic destination for human explorers. It is close by cosmic standards. But even Mars is far enough away that a journey can take many months. The planet moves continuously around the Sun, just as Earth does. A spacecraft cannot simply point toward where Mars appears and travel in a straight line. It must aim toward the location the planet will occupy in the future. The voyage becomes a meeting between moving worlds. By the time we pass Mars, Earth is no longer recognizable without instruments. The Sun still dominates the sky, but the home planet has faded into the background. Ahead, the asteroid belt stretches between Mars and Jupiter. Popular imagination often portrays it as a crowded field of tumbling rocks, forcing spacecraft to dodge between giant objects. The reality is quieter. The asteroids are widely separated. Most of the region remains empty. A spacecraft could pass through without seeing a large asteroid nearby. Yet the belt contains an enormous history. Fragments left from the formation of the solar system. Bodies that never became a planet. Rock, metal, ice and dust moving through ancient orbits. Some are tiny. Others are hundreds of kilometers wide. Ceres, the largest object in the belt, is massive enough to become nearly round under its own gravity. These worlds are not merely debris. They are preserved pieces of the early solar system. Our journey would pass through them quickly compared with the age they contain. Beyond the asteroid belt, Jupiter appears. At first, it looks like a bright point, then a disk, then a world so large that it begins to dominate the view. Jupiter is not simply another planet. It is a system. Its gravity controls dozens of moons. Its magnetic field extends far into space. Its storms have lasted for centuries. The Great Red Spot alone is wider than Earth. Clouds rotate in bands around the planet, driven by internal heat and rapid rotation. Lightning flashes through deep storms. Radiation surrounds the world. Jupiter marks the beginning of the outer solar system, where everything becomes larger and more distant. Its moons appear like a miniature collection of planets. Io is covered in active volcanoes. Europa hides an ocean beneath ice. Ganymede is larger than Mercury. Callisto preserves an ancient surface marked by impacts. A traveler could spend years exploring only this one planetary system. But our destination lies farther. We continue outward. Jupiter begins to shrink behind us. The Sun becomes smaller. Its light weakens. The darkness between worlds grows deeper. Saturn eventually appears, surrounded by rings so thin and wide that they seem impossible. From a distance, they form smooth bands. Up close, they separate into countless particles of ice and rock. The rings may be the remains of a moon destroyed by gravity or collision. They are beautiful because we see the destruction from far away. Saturn's moons add another collection of mysteries. Titan possesses rivers, lakes, clouds, and rain made from hydrocarbons. Enceladus sends water-rich plumes into space from a hidden ocean. The farther we travel from Earth, the less familiar the solar system becomes. The planets are no longer simple points moving around the Sun. Each one is surrounded by its own environment, its own history, and its own collection of worlds. Past Saturn, the distances become more difficult to feel. Uranus waits far beyond. Its pale blue atmosphere conceals a planet rotating almost completely on its side. Its rings are dark. Its moons follow tilted paths. The Sun is now only a fraction of the size it appeared from Earth. A full orbit around the star takes Uranus more than 80 Earth years. A season there can last decades. The outer solar system does not experience time the way we do. Every movement is slower. Every orbit is longer. Every mission requires patience. Neptune lies farther still. Its atmosphere contains some of the fastest winds known in the solar system. Dark storms appear and disappear. Clouds of frozen material race through a deep blue atmosphere. Its moon Triton moves backward around the planet, suggesting that it may have been captured from another region of the solar system. From Neptune, the Sun appears as an extremely bright star rather than the enormous disk that warms Earth. Solar energy is weak. Temperatures are low. The inner planets are hidden near the distant sunlight. Yet Neptune is not the edge. For much of human history, the planets seemed to define the solar system. Once the last planet was passed, it was easy to imagine that interstellar space began immediately. But the Sun's domain extends much farther. Beyond Neptune lies the Kuiper Belt, a wide region containing icy bodies, dwarf planets, and remnants from the solar system's formation. Pluto belongs to this distant population. It was once treated as a solitary world at the edge of the planetary system. Now we know it is part of a much larger landscape. Pluto itself is unexpectedly complex. It has mountains made of water ice, a vast heart-shaped region containing frozen nitrogen, glaciers moving slowly across the surface, a thin atmosphere that expands and contracts as the dwarf planet moves around the Sun. Its largest moon, Charon, is so large relative to Pluto that the two worlds appear almost like a double system. The flyby of Pluto revealed something important. Distance does not mean simplicity. Even at the edge of sunlight, worlds remain active, layered, and surprising. Farther into the Kuiper Belt, many objects remain undiscovered. Some follow stable paths, others travel through stretched or tilted orbits. Their surfaces preserve ancient chemistry. Their movements reveal the gravitational history of the solar system. A spacecraft passing through this region would still be traveling among objects controlled by the Sun. But the spaces between them would be vast. Years could pass without a close encounter. The Sun would remain visible behind us, bright enough to identify, small enough to feel far away. Eventually, the Kuiper Belt would thin. But the journey outward would continue. The next boundary would not be visible. There would be no wall, no sign, no sudden change in the darkness. Yet the spacecraft would be approaching the edge of a bubble created by the Sun. The Sun releases a continuous flow of charged particles called the solar wind. These particles move outward in every direction. They pass the planets. They interact with magnetic fields. They carry part of the Sun into space. Together, they create an enormous region called the heliosphere. The planets travel inside this bubble. Earth is protected within it. Even Neptune remains deep inside the Sun's extended influence. But the solar wind cannot expand forever without resistance. Far from the planets, it begins interacting with the material between stars. The outward flow slows, its pressure weakens. Eventually, a boundary forms where the solar wind can no longer dominate. This region is known as the heliopause. Crossing it means entering interstellar space. Only a few human-made objects have traveled far enough to reach that boundary. Their journeys required decades. That fact alone reveals the scale. A spacecraft can pass every known planet and still need many more years to reach the true edge of the Sun's protective bubble. As we approach the heliopause, the environment changes. Particles from the Sun become less dominant. Cosmic rays from the galaxy become more common. Magnetic fields shift. The density of surrounding plasma changes. None of this would create a dramatic view through a window. Interstellar space does not appear as a glowing ocean. It remains dark. Stars continue shining in the distance. The Sun remains behind us. But instruments would know that something important had happened. We would have crossed from the space shaped primarily by our star into the wider environment of the Milky Way. For the first time, we would truly be between the stars. Yet even now, we would not be outside the solar system in every possible sense. Far beyond the heliopause, scientists believe a vast cloud of icy bodies surrounds the Sun. The Oort cloud. It has never been photographed directly as a complete structure. Its existence is inferred from the long paths of comets that occasionally fall toward the inner solar system. These comets may spend millions of years in distant darkness before a gravitational disturbance changes their motion. A passing star. The pull of the galaxy. Interactions with other objects. A tiny change can send one inward toward the Sun. The Oort cloud may begin thousands of times farther from the Sun than Earth. Its outer region may extend a significant fraction of the distance to the nearest stars. If we traveled through it, we would not see a bright shell of ice. The objects would be separated by enormous distances. The region would appear almost completely empty, yet somewhere in the darkness, frozen worlds would continue orbiting the Sun, small bodies preserving material from the birth of the solar system. The Sun's most distant family. Crossing the Oort cloud could take thousands of years with current spacecraft speeds. This is where the meaning of leaving the solar system becomes complicated. We can cross the heliopause and enter interstellar space. But the Sun's gravity continues influencing objects much farther away. Its domain fades gradually. There is no single simple edge. The solar system becomes weaker, thinner, and more difficult to define until the surrounding galaxy takes over. Once the last distant comets are behind us, the Sun becomes another star. Perhaps still the brightest in that region, but no longer a special disk in the sky. Earth would be invisible. Jupiter, Saturn, and Neptune would be hidden in the Sun's light. The entire solar system would collapse into one small point. A distant observer might not know that 8 planets orbit it. They might not know that one world contains oceans and cities. They might not know that a species once looked outward from that system and imagined this journey. All signs of home would disappear into starlight. The nearest neighboring star system, Alpha Centauri, lies more than 4 light-years away. Light leaving the Sun needs more than 4 years to reach it. This means that even at light speed, the journey would not be immediate. At the speed of our fastest probes, the voyage would require many thousands of years. The gap between stars is not simply larger than the gap between planets. It belongs to a different scale entirely. If the Sun were a small object placed in one city, the nearest star would be in another city far beyond the horizon. Between them would be almost nothing. No convenient planets, no fuel stations, no natural shelters, only sparse atoms, dust, radiation, magnetic fields, and darkness. The stars appear close together in the night sky because we view them from an enormous distance. Their light is projected onto the same dark background, but in space, They are separated by vast three-dimensional distances. A constellation is not a true group of neighboring stars. Its shape exists only from our position. The stars forming the pattern may lie hundreds of light-years apart. If we traveled between them, the familiar constellations would slowly distort. Orion would lose its shape, the Big Dipper would stretch and break. The night sky is not permanent. It is a temporary perspective created by our location and our moment in galactic history. As we move away from the sun, the stars would shift. Some would brighten as we approach them, others would fade behind us. The geometry of the sky would change. For the first time, we would see our stellar neighborhood from outside the viewpoint of Earth. Alpha Centauri would eventually separate into its true components. Two sun-like stars orbiting one another, with the smaller red dwarf Proxima Centauri located farther away. Proxima is the nearest individual star to the Sun. It is small, dim, and active, a red dwarf producing powerful flares. At least one planet orbits within a region where temperatures could, under the right conditions, allow liquid water. But distance from the star is only one condition for habitability. Radiation, atmosphere, magnetic protection, tidal locking, and planetary history all matter. The nearest potentially rocky world may still be completely hostile. This would become a repeating lesson during our journey. Planets may be common. Earth-like conditions are harder. Life may require a delicate combination of stability, chemistry, energy, and time. A world can orbit at the right distance and still lose its atmosphere. Another may possess water beneath ice but no open surface. Another may be rich in organic material without ever becoming alive. The universe contains possibility everywhere, certainty almost nowhere. Beyond Alpha Centauri, the nearby stars form a loose neighborhood. Barnard's star, Sirius, Epsilon Eridani, Tau Ceti. Small red dwarfs too faint to see without instruments. Bright stars whose light has guided human navigation. Each one moves through the galaxy independently. Each may possess planets. Some systems may contain debris disks, comets, asteroids, and worlds still waiting to be discovered. But even this local neighborhood spans dozens of light years. A map showing nearby stars may look crowded. In reality, every point is separated by years of light travel. Communication between them would be slow. Travel would be slower. A civilization spreading from one star to another would need to think in generations. The galaxy does not make movement impossible. It makes movement expensive in time. This difference matters. A place can be physically reachable and still remain practically distant. The speed of light forms the deepest boundary. Nothing carrying information can move faster through ordinary space. Even if future humans created spacecraft moving at a significant fraction of that speed, the nearest stars would still require years. More distant destinations would require decades, centuries, or longer. The universe forces travelers to respect distance. There is no universal presence shared across the galaxy. When we look at a star 50 light-years away, we see it as it was 50 years ago. If someone there looked at Earth, they would see our planet's past. Every observer lives inside a bubble of delayed information. The farther we see, the older the image becomes. This means that traveling outward is also traveling into a landscape of different times. A star may appear bright even if it has already changed. A distant world may appear peaceful even if its atmosphere was lost years ago. Civilization could send a signal, disappear, and have its message continue traveling long after its end. Space preserves the past through light. our journey would move through these delayed views. The universe ahead would never appear exactly as it is at the moment we observe it. It would appear as it was when its light began traveling toward us. This becomes increasingly important as the distances grow. Within the local stellar neighborhood, the delay is measured in years or decades. Across the Milky Way, it becomes thousands or tens of thousands of years. Across the universe, it becomes millions or billions. To travel through space is to travel through a museum of ancient light. But before we reach distant galaxies, we must first understand the one surrounding us. The Milky Way. From Earth, it appears as a faint band crossing the night sky. For people living under dark conditions, the band can be bright enough to cast a subtle glow. It is not a cloud inside our atmosphere. It is the combined light of countless stars seen from within the disk of our galaxy. We live inside the Milky Way, so we cannot step outside and photograph it directly. Every complete image of our galaxy is a scientific reconstruction or an artistic interpretation based on observations. Yet measurements reveal its broad structure: a barred spiral galaxy. A bright central region, curving arms filled with stars, gas, and dust, a vast halo surrounding the disk. The Sun lies far from the center, inside a smaller structure often called the Orion Spur. We are not at the heart of the galaxy. We are not at the outermost edge. We occupy an ordinary region between major spiral arms. This location helped shape our view of the universe. Dust blocks much of the visible light toward the galactic center. From Earth, we see only part of the Milky Way clearly. Radio, infrared, and other wavelengths allow telescopes to look through the dust and map the hidden galaxy. If our spacecraft continued outward from the Sun, the Milky Way would not immediately become visible as a spiral. We would need to travel an enormous distance above or below the galactic disk before seeing the full shape clearly. The galaxy is about 100,000 light-years wide, perhaps more depending on how its faint outer structure is measured. Its disk contains hundreds of billions of stars. The Sun is only one of them. The distance from our system to the galactic center is roughly 26,000 light-years. Light leaving Earth during the earliest stages of human civilization would still not have reached the center today. That is the scale of our own galaxy. The Milky Way feels like home. But it is already almost beyond imagination. Our entire journey from Earth, past every planet, across the heliopause, through the Oort cloud and toward the nearest stars would represent almost no movement on a galactic map. We would have crossed enormous distances and still remained beside the Sun. This is the first great lesson of traveling beyond the universe. Every boundary opens onto a larger scale. Earth gives way to the solar system. The solar system gives way to the stellar neighborhood. The stellar neighborhood gives way to the Milky Way. And the Milky Way is only one galaxy among an unimaginable number. For now, our spacecraft continues into the darkness between nearby stars. Behind us, the Sun has become another point of light. Ahead, the Milky Way surrounds us in every direction. We have left our planet. We have crossed the domain of our star, but we are still deep inside our galactic home. The true journey beyond the universe has barely begun. To understand what it would mean to travel beyond the Milky Way, we must first cross a galaxy so large that nearly every journey humanity has ever imagined becomes insignificant inside it. From our position near the Sun, the galaxy surrounds us. There is no obvious wall, no bright border, no single direction marked outward. Stars appear in every part of the sky because we are embedded inside a vast rotating disk. Gas, dust, stellar clusters, dead stars, planets, and invisible dark matter all move together under the gravity of the Milky Way. Our first challenge would be choosing a path. Traveling toward the galactic center would lead into regions of increasing density. Traveling outward through the disk would eventually take us beyond the major spiral arms. Moving above or below the disk would offer the shortest path toward a clearer view of the galaxy's overall shape. For this journey, we turn away from the crowded plain. The spacecraft begins climbing above the Milky Way. There is no true upward direction in space, but relative to the galactic disk, we move toward a region where the stars gradually become less concentrated. At first, very little appears to change. The Sun remains one star behind us. Nearby systems continue passing slowly. The familiar bright band of the Milky Way begins shifting beneath the spacecraft, but the galaxy is so enormous that even moving at impossible speeds would require patience before the structure became obvious. The disk is not a flat sheet. It has thickness. Young stars, clouds of gas, and regions of active star formation remain concentrated near the central plane. Older stars occupy wider orbits above and below it. Dust clouds create dark lanes that block visible light. Stellar streams pass through the region, remnants of smaller systems absorbed by the Milky Way over its history. As we rise, the galaxy begins separating into layers. Below us, the brightest stars form an increasingly dense field. Clouds of gas trace parts of the spiral arms. Dark regions reveal where dust hides the light behind it. The Sun's neighborhood becomes impossible to identify with the human eye. Our home system is now one point among billions. Even knowing its exact location would require careful navigation. This is one of the first emotional changes of the journey. Earth does not merely become distant, it becomes lost inside a crowd. From within the solar system, the Sun is the center of everything. From outside the local neighborhood, it has no obvious visual importance. There is no beam pointing back toward home. No unique color separating it from the surrounding stars. Without instruments and records, a traveler could look directly toward the solar system and never know which tiny light contained the world where humanity began. As the spacecraft continues, the Milky Way's spiral form emerges slowly. We begin to see that the arms are not solid structures made from the same stars permanently traveling together. They are patterns, regions where gas becomes compressed, where star formation becomes more active, and where bright young stars briefly illuminate the shape of the galaxy. Individual stars can move into and out of a spiral arm during their orbits. The arm remains visible even though its contents change. It is similar to a traffic jam on a highway. Cars enter the dense region, move through it, and eventually leave, while the pattern of congestion remains. The Milky Way's arms are far more beautiful, but the principle helps explain how a structure can persist while its individual stars continue moving. Bright blue stars highlight the arms, because they are massive and short-lived. They do not survive long enough to travel far from the regions where they formed. Their light marks places where gas clouds recently collapsed. Redder and older stars are spread more widely throughout the disk. This means the dramatic spiral pattern represents only part of the galaxy's population. Much of the Milky Way is quieter, older, dimmer, and more difficult to see. Between the major arms are vast regions containing stars, planets, and dark clouds. They are not empty. But they appear less brilliant because fewer massive stars are illuminating them. The galaxy contains cities of light and long regions of comparative darkness. Our own location inside a smaller spur is one such region, not at the center of activity, not completely isolated, a relatively calm neighborhood inside a much larger structure. As we travel higher, the galactic center becomes more visible. It shines as a dense concentration of stars near the middle of the disk. From Earth, dust hides much of this region. From our new viewpoint, the central bulge appears brighter and more complex. Millions of stars occupy a volume far more crowded than our local neighborhood. The distances between them can be much smaller. The night sky from a planet near the galactic center could look dramatically different from ours. Stars might fill the darkness. The glow of the surrounding galaxy could remain visible even without a moon, yet beauty would come with danger. The central region contains more radiation sources, more stellar remnants, more close gravitational encounters, more supernovae over long periods. Planetary systems may face disturbances from passing stars. A world there would exist inside a busier and potentially less stable environment. At the heart of the Milky Way lies an object that cannot be seen directly. A supermassive black hole called Sagittarius A star. It contains millions of times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. The black hole itself produces no light, but stars orbit it at extraordinary speeds. Gas becomes heated as it moves through the central environment. Powerful telescopes have tracked stars circling an apparently empty point, revealing the mass hidden there. One star completes an orbit in only a few years, accelerating as it approaches the black hole and slowing as it moves away. These stellar motions allow scientists to map gravity around an object that remains invisible. From our distant path above the disk, the central black hole would not appear as the giant dark portal often shown in illustrations. The surrounding stars would dominate the view. The event horizon would be far too small to see without extraordinary instruments. Yet the black hole's influence would be clear through motion. The center of the galaxy is organized around hidden mass. The Milky Way rotates not because of the black hole alone, but because of the total gravity of stars, gas, dust, and dark matter spread through the galaxy. The black hole is important locally. The larger galaxy depends on a much broader distribution of matter. This distinction matters because the Milky Way contains much more than what glows. If we measured the movement of stars, we would find that the visible material cannot fully explain their speeds. Stars far from the center move too quickly to remain bound if the galaxy contained only the matter we can see. Something else contributes gravity. We call it dark matter. It does not appear to emit or reflect light. It does not form glowing clouds or ordinary planets. But its gravitational effects shape galaxies. The Milky Way is believed to sit inside a vast halo of dark matter extending far beyond the bright stellar disk. This means leaving the visible galaxy would not mean leaving the galaxy's full gravitational structure. The stars may thin, the spiral arms may end. But the invisible halo continues. Our spacecraft could travel far above the disk and still remain inside the Milky Way's gravitational domain. The galaxy is larger than its light. This becomes more obvious as the full shape comes into view. The bright disk appears thin compared with its width. The central bar stretches through the middle. Spiral arms curve outward. Dust creates dark filaments. Faint stars extend beyond the main visible edge. Around everything lies an enormous, mostly invisible halo. Embedded within that halo are globular clusters. These are ancient spherical collections containing hundreds of thousands or even millions of stars. They orbit the Milky Way far above and below the disk. Some are nearly as old as the galaxy itself. From a distance, a globular cluster appears like a compact ball of light. Inside, stars are crowded together much more closely than in the solar neighborhood. A planet within such a cluster could see a sky filled with brilliant neighboring suns. But stable planetary systems may face challenges from frequent gravitational encounters. Passing stars could disturb distant comets or alter wide planetary orbits. The cluster is beautiful because of its density. The same density creates instability. These clusters preserve evidence from the early Milky Way. Their stars formed when the universe contained fewer heavy elements. Later generations of stars were enriched by material created in stellar interiors and supernova explosions. Elements such as carbon, oxygen, silicon, and iron were forged through earlier stars and spread through space when those stars died. The Sun formed from gas already enriched by previous generations. Earth, our bodies, and the spacecraft itself are made from material processed inside ancient stars. As we pass above the galaxy, this fact becomes visible on a grand scale. The Milky Way is not simply a collection of stars born independently. It is a recycling system. Gas collapses, stars form, they create new elements, they release material. New clouds gather, new stars and planets appear. The galaxy changes through repeated cycles of birth, transformation, and return. Our spacecraft is made from the result of that history. Metal refined on Earth originated in ancient stellar explosions. Carbon in the materials once passed through stars. The traveler is not foreign to the galaxy. It is a rearrangement of galactic matter moving through its own place of origin. Beyond the globular clusters, other structures appear. Long streams of stars curve around the Milky Way. These are remnants of smaller galaxies and clusters pulled apart by gravity. The Milky Way did not form peacefully. It grew by absorbing other systems. A dwarf galaxy approaches. Tidal forces stretch it. Stars are removed. Its original shape dissolves. The stolen stars become streams orbiting the larger galaxy. Over time, the smaller system loses its identity. The Milky Way becomes slightly larger. This process has happened many times. It is still happening. Several dwarf galaxies orbit the Milky Way today. Some may eventually merge with it. Their stars will join the larger galactic population. Their gas may contribute to new star formation. Their dark matter may become part of the Milky Way's halo. Our galaxy is therefore not a finished object. It is still growing, still interacting, still carrying evidence of earlier collisions. From Earth, the Milky Way feels permanent. From outside, it appears more like a living history of mergers, disruptions, and slow gravitational rearrangement. The spiral disk may look elegant, but the halo contains the remains of ancient destruction. Beauty again emerges from violence spread across time. As we continue farther, the Milky Way shrinks behind us. For the first time, we can imagine seeing the galaxy as a complete object. A bright spiral island suspended in darkness. The view would be unlike any photograph from Earth because no human spacecraft has traveled far enough to capture it. What we imagine is based on measurements, comparisons with other galaxies, and reconstructions. Still, the broad scene is powerful. A disk of stars tens of thousands of light-years wide, a central glow, spiral arms marked by young stars, dark lanes of dust, faint outer regions fading into the halo, and somewhere inside one minor spur, a sun too small to identify. The entire human story occupies no visible fraction of the image. This is the scale where civilizations disappear. A planet containing billions of people contributes almost nothing to the brightness of a galaxy. Cities do not change its appearance. Radio signals weaken as they expand. Spacecraft become invisible almost immediately. From outside, the Milky Way does not reveal that humanity exists. It does not reveal whether any civilization exists. A galaxy can contain countless inhabited worlds and still look like a silent spiral of light. This helps explain one of the great difficulties in searching for intelligence. Life may be present without changing the galaxy in an obvious way. A civilization might remain confined to one planet. Another might use technology that produces signals too weak or too brief for distant observers. Another may have existed thousands of years ago, leaving no transmissions still crossing our path. The Milky Way is large enough to hide activity within its own scale. Our spacecraft passes into the galactic outskirts. Stars become rarer. The bright disk now occupies only part of the sky. Ahead lies a darkness far deeper than the spaces between nearby stars. We are approaching intergalactic space, but leaving the Milky Way is not as simple as crossing the last visible star. The galaxy's gravity continues pulling. To escape permanently, the spacecraft must move faster than the local escape velocity. This speed depends on location and on the galaxy's total mass, including the dark matter halo. A slow traveler might move beyond the disk and still remain gravitationally bound. It would follow a huge orbit and eventually return toward the galaxy. True escape requires enough energy to break free from the entire system. Our imagined spacecraft possesses that energy. It continues outward. Behind us, the Milky Way gradually becomes smaller. Individual spiral details fade. The galaxy turns into a bright object similar to the distant galaxies seen through telescopes from Earth. At first, the darkness ahead appears empty. Then other members of the local group become easier to recognize. The Milky Way is not alone. It belongs to a small collection of galaxies held together by gravity. The largest members are the Milky Way and Andromeda. A third spiral galaxy, Triangulum, is smaller but still contains billions of stars. Dozens of dwarf galaxies move through the group. Some orbit larger galaxies, others occupy more distant paths. The local group extends across millions of light years. It is our true galactic neighborhood. On a map of the observable universe, it is tiny. From within it, the distances remain overwhelming. Andromeda is the most prominent destination ahead. From Earth, it can appear as a faint patch of light under dark skies. That small patch is an entire galaxy larger than the Milky Way in visible extent. Its light has been traveling for more than 2 million years before reaching Earth. When our ancestors first began developing early human traits, some of the photons entering our telescopes today were already crossing intergalactic space. The galaxy we observe is ancient information. Andromeda, as it exists now, will not be visible from Earth for millions of years. Our imagined journey crosses this delay. As we approach, the galaxy grows. The faint patch becomes an enormous spiral. Dust lanes curve around its center. Star-forming regions glow through the disk. Satellite galaxies orbit nearby. The scale becomes clear only gradually. From far away, the entire galaxy can fit within a telescope's field of view. From close range, traveling across it would require tens of thousands of years, even at light speed. A galaxy is easy to see as one object only because it is impossibly far away. Closeness destroys simplicity. As we approach Andromeda, the spiral separates into billions of stars. The smooth glow becomes a population. What looked like one object becomes countless worlds, each moving through its own local environment. This is the same transformation we experienced when leaving Earth. At a distance, systems look simple. Up close, every layer reveals complexity. Andromeda contains a central supermassive black hole. It contains clusters, dust, gas, stellar remnants, and perhaps enormous numbers of planets. It may contain civilizations. It may contain life that began and ended before humanity appeared. We have no way to know. The light reaching us carries only the broad appearance of the galaxy. It does not reveal conversations, cultures, or minds. Even if a civilization transmitted a signal toward the Milky Way today, the message would require more than 2 million years to arrive. By then, the sender might no longer exist. The receiver might no longer exist. Communication between galaxies is not simply slow. It operates on evolutionary timescales. A species can emerge, change, and disappear before one message crosses the gap. Intergalactic communication would be less like a conversation and more like archaeology carried by light. A civilization sends evidence into space. Another civilization discovers it millions of years later. No reply can matter to the original sender. The exchange becomes one way across time. This gives the distance between galaxies a different emotional quality from the distance between stars. Stars may be separated by years of light travel. Galaxies are separated by millions. Within the Milky Way, a civilization might still imagine reaching nearby systems across generations. Between the Milky Way and Andromeda, the journey becomes larger than recorded human history multiplied many times. Even a spacecraft traveling close to light speed would carry its passengers into a future beyond recognition. Earth would change. The sun would age. Civilizations could rise and fall. The traveler might arrive in a galaxy that no longer matches the light seen at departure. And yet, the Milky Way and Andromeda are moving toward each other. Gravity has linked their futures. In several billion years, the two galaxies are expected to interact and eventually merge. The word collision may create the image of stars crashing together. But stars are separated by such large distances that direct collisions would remain rare. The galaxies would pass through one another. Gravity would distort their shapes. Long streams of stars would be pulled outward. Gas clouds could collide and trigger new star formation. The central black holes might eventually move toward one another and merge. The night sky from a surviving planet would become extraordinary. Andromeda would grow larger over millions of years. Its disk would spread across the sky. New arcs and streams of stars would appear. The familiar shape of the Milky Way would change. Eventually, the two spirals could settle into a larger, more rounded galaxy. The merger would transform our galactic neighborhood without necessarily destroying every planetary system. The Sun itself may be moved into a different orbit. It could end up farther from the center, or thrown into another region. The exact future cannot be predicted perfectly because so many gravitational interactions are involved. What is clear is that galaxies are not isolated permanent islands. They move, they interact, they combine. The local group is slowly becoming one larger structure. Our spacecraft's journey through this region reveals a future already written partially by gravity. Andromeda and the Milky Way appear separate today only because we are watching an early stage of the relationship. Given enough time, the distance between them will disappear. This reminds us that cosmic maps are temporary. The universe does not preserve arrangements for observers. Galaxies change position, groups merge, clusters evolve, expansion separates distant structures. Any map represents only one moment. As we move beyond Andromeda, the local group begins to take shape behind us. Several major galaxies surrounded by faint dwarfs, a collection occupying a region millions of light-years wide. Beyond it lies a wider environment. The local group is part of a much larger pattern containing groups, clusters, filaments, and voids. Galaxies are not scattered randomly. Gravity has organized matter into an immense cosmic web. Dense regions contain clusters with hundreds or thousands of galaxies. Long filaments connect them. Between the filaments lie enormous voids containing far fewer galaxies. From a sufficient distance, the universe resembles a network. Bright threads surrounding vast dark spaces. The pattern began from tiny differences in density in the early universe. Regions containing slightly more matter attracted additional material. Gravity amplified the differences. Gas collapsed. Galaxies formed. Clusters grew. Less dense regions lost matter and became emptier. Across billions of years, small variations became the largest structures in existence. Our next destination lies beyond the local group, toward a nearby collection of galaxies called the Virgo Cluster. It is tens of millions of light-years away. The distance makes the crossing between the Milky Way and Andromeda seem small by comparison. As we travel, the local group shrinks behind us. Individual galaxies blend into a faint collection. Ahead, the Virgo Cluster gradually brightens. At first, it appears as several distant points, then dozens, then hundreds. A cluster is not simply a crowded image of unrelated galaxies. Its members are held together by gravity. They move through a shared environment containing hot gas and dark matter. Large elliptical galaxies dominate the central region. Spiral galaxies orbit farther out. Smaller systems move between them. Some galaxies experience close encounters. Their shapes distort. Gas is stripped away. Star formation can be reduced or triggered depending on the interaction. The cluster environment changes the lives of galaxies. A galaxy entering the cluster may lose gas as it moves through hot material between galaxies. Without fresh gas, it forms fewer new stars. Its bright blue star-forming regions fade. The galaxy ages. Others merge with neighboring systems. Some are stretched into long tails. A cluster is not a peaceful gathering. It is an ecosystem governed by gravity, motion, and collision. The individual galaxies remain separated by enormous distances, but compared with the emptiness elsewhere, they are densely packed. The night sky from a planet inside such a cluster could contain many visible galaxies. Some might appear large enough to reveal structure without a telescope. The universe there would look more crowded than it does from Earth, yet the distances would still make travel nearly impossible. Seeing many galaxies does not make them close. The cluster's total mass bends the path of light. This creates gravitational lensing. Galaxies behind the cluster may appear stretched into arcs. Multiple images of the same distant object can appear in different places. The cluster acts as a natural cosmic lens. Its gravity changes what observers see. By studying these distortions, scientists can map mass that does not emit light directly. Once again, dark matter reveals itself through influence rather than appearance. The visible galaxies account for only part of the cluster's gravity. Much of the mass lies in an invisible component spread through the structure. Hot gas also fills the space between galaxies. It can reach extreme temperatures and shine in X-rays. This means intergalactic space inside a cluster is not completely empty. It contains a thin, hot atmosphere extending across millions of light years. Galaxies move through it. Explosions and central black holes inject energy into it. Heavy elements created by stars spread through it. The cluster becomes a vast environment with weather of a different kind. Not clouds and rain. Gas flows, shocks, magnetic fields, and gravitational interactions across distances larger than galaxies. From within the Virgo cluster, the universe feels full again. Galaxies appear in many directions. But once we leave it, the darkness returns. Ahead lies one of the great voids, a region where galaxies become rare. The transition is gradual. The cluster fades behind us. The nearest bright systems grow more distant. The spacecraft enters an expanse where matter is thinly distributed. The cosmic web surrounds voids that can span hundreds of millions of light years. These are not perfectly empty holes. They contain some galaxies, gas, dark matter, and radiation. But compared with filaments and clusters, they are sparse. Traveling through one would create the deepest isolation imaginable. The Milky Way could no longer be seen without powerful instruments. The Virgo cluster would fade. Ahead, the next filament might remain millions of light years away. Every direction would contain ancient light from distant structures, but the local region would offer almost nothing. A planet inside such a void, if one existed, might see far fewer nearby galaxies. Its astronomers could have greater difficulty discovering the large-scale structure of the universe. Their cosmic environment would look emptier. The place from which an observer studies reality shapes what reality seems to be. Humanity lives inside a galactic group near larger structures. This gives us a view rich enough to reveal the cosmic web. Another civilization could evolve in a much more isolated region and reach different early conclusions. Our journey through the void reveals another important truth. The universe can contain enormous structures while remaining mostly empty. Galaxies occupy only a tiny part of the volume. Stars occupy even less. Planets are smaller still. Matter gathers into islands surrounded by distances that dominate everything. The farther we travel, the more the universe appears to be made not from objects, but from the space separating them. And yet this empty space is not nothing. It contains fields, radiation, rare particles, the expansion of the universe. Perhaps dark energy, the name given to whatever is causing cosmic expansion to accelerate. Space itself participates in the evolution of the cosmos. The distance between distant galaxies grows because the fabric of the universe expands. This is not the same as galaxies flying through static emptiness from one central explosion. There is no known center of expansion within ordinary space. From any large-scale location, distant galaxies appear to move away. The space between unbound structures increases, the cosmic web stretches. Clusters held together by gravity remain intact, but widely separated groups move farther apart. As our spacecraft crosses the void, this expansion becomes one of the most important forces shaping the journey ahead. We are no longer traveling only across distance, we are traveling through distance that continues growing. The universe beyond the local group is not waiting in a fixed arrangement, it is receding. The farther a galaxy lies, the faster the space between us, and that galaxy tends to expand. At sufficiently great distances, objects can become unreachable even by a traveler moving at light speed, not because they locally move through space faster than light, but because the intervening space grows too rapidly. This creates a cosmic limit. Some galaxies visible today can never be reached. Their ancient light arrives from a time when they were closer. The regions where they now exist are already being carried away beyond any future journey. We can see them, but we cannot visit them. The observable universe is larger than the reachable universe. That distinction will define everything ahead. Our spacecraft leaves the void and approaches another filament of the cosmic web. Galaxies appear again. Groups become clusters. The structure extends across the darkness like a glowing thread. But behind us, the Milky Way has become completely insignificant. Our galactic home is now one faint point among countless others. We have crossed from a planet to a solar system, from a solar system to a galaxy, from a galaxy to a group, from a group into the wider cosmic web. And still, we remain far inside the observable universe. The true boundary lies beyond every cluster we can see, beyond structures whose light has traveled billions of years, beyond a distance where looking outward becomes the same as looking backward toward the beginning of cosmic history. Our journey has left the Milky Way behind. But the universe ahead is larger than anything we have crossed so far. And from this point onward, distance will no longer be the only barrier. Time itself will begin closing the road. The farther we travel from the Milky Way, the more the universe changes from a landscape into a history. Nearby galaxies appear almost modern. Their stars resemble the stars around us. Their structures are familiar. Spiral arms, elliptical shapes, bright regions where new suns are forming, dark lanes of dust. But as our journey continues across billions of light years, the galaxies ahead begin to look different, not because distance is changing them, because distance is revealing them as they once were. Every object in the sky is observed through delayed light. The moon appears as it was slightly more than a second ago. The sun appears as it was several minutes ago. Nearby stars appear years or decades in the past. Andromeda appears more than 2 million years ago. The deepest galaxies appear billions of years before Earth existed. There is no way to look across the universe without looking backward in time. Light becomes the memory of space. Our imaginary spacecraft is moving outward through this memory. Behind us lies the present-day cosmic web. Ahead lies an increasingly ancient universe. At first, the change is subtle. Galaxies become slightly smaller. Their light becomes redder. Some appear distorted because their photons have been stretched during the journey. The universe has expanded while the light was traveling. A wave that began shorter arrives longer. Blue light may shift toward red. Visible light may stretch into infrared. Ultraviolet light can become visible or infrared by the time it reaches our instruments. This process is called cosmological redshift. It is one of the great tools for measuring the distant universe. The redder the light has become, the more the space between the source and observer has expanded during its journey. Redshift is not merely a color change. It is evidence that the universe itself has evolved while the photons crossed it. A distant galaxy sends light into space. The light begins traveling. Then the distance expands. The wavelength stretches along with it. By the time the signal arrives, the universe has changed both the message and the separation. As we travel farther, this redshift becomes stronger. Galaxies that once emitted bright visible light now glow mainly in wavelengths human eyes cannot detect. Without infrared instruments, they would disappear. The universe does not end when visible light fades. Our eyes simply lose access to it. This is why modern telescopes must observe more than one part of the electromagnetic spectrum. Radio waves reveal cold gas and distant activity. Infrared light passes through dust and shows ancient galaxies. X-rays reveal extremely hot matter near black holes and clusters. Different wavelengths expose different layers of reality. A universe seen only by human eyes would be incomplete. Our spacecraft carries instruments capable of translating these hidden signals into images. Ahead, clusters of galaxies appear through stretched infrared light. Some lie so far away that their current condition is unknowable. We are seeing them before the Sun formed, before the Milky Way reached its present structure, before many of the heavier elements needed for planets had become common. The cosmos around them was younger, denser, and more active. Galaxies collided more frequently. Gas was more abundant. Stars formed at higher rates. Supermassive black holes consumed material rapidly. The distant universe was not a quieter version of the present. It was often more violent. As we enter these ancient regions, quasars begin appearing. A quasar can outshine an entire galaxy, even though its energy comes from a relatively small central region. At its heart lies a supermassive black hole. The black hole itself remains dark, but gas falling toward it forms a rapidly rotating disk. Friction and compression heat the material to extreme temperatures. Radiation is released across enormous distances. Jets may emerge from the environment near the black hole, carrying energy far beyond the host galaxy. From Earth, a quasar can look like a single bright point. Its name came from its star-like appearance. But it is not a star. It is the brilliant center of a distant galaxy, powered by matter falling toward a black hole millions or billions of times more massive than the Sun. Some of the quasars we observe existed when the universe was still very young. This creates a mystery. How did such enormous black holes grow so quickly? A black hole can gain mass by consuming gas and merging with other black holes, but growth takes time. Finding extremely massive examples early in cosmic history suggests that some may have begun from unusually heavy seeds or experienced periods of rapid feeding. Perhaps the first generations of stars collapsed into black holes. Perhaps dense gas clouds formed larger black holes directly. Perhaps repeated mergers built them faster than expected. The exact story remains uncertain, but quasars reveal that the young universe produced giants early. A civilization living near one would see a very different sky. The galactic center might shine with intense radiation. Jets could extend far beyond the host galaxy. Gas would be heated, pushed outward, or prevented from forming stars. The central black hole would influence the future of the entire galaxy. It could limit growth by driving material away. It could also compress gas and trigger star formation in certain regions. A black hole is not simply an object consuming whatever approaches. Its activity can shape its surroundings across hundreds of thousands of light years. This relationship between black holes and galaxies appears throughout cosmic history. Large galaxies almost always contain massive central black holes. The masses of the black holes seem connected to the properties of the surrounding galaxies. They may grow together. When galaxies merge, their central black holes can eventually approach one another. They orbit, lose energy, move closer. Finally, they merge and send gravitational waves through the universe. These waves are ripples in space-time itself. They do not travel through space like ordinary sound. They are distortions of space carrying information about enormous accelerating masses. A merger between supermassive black holes could produce signals stretching across the cosmos. Long after the galaxies lose their original shapes, the gravitational disturbance continues outward. The universe carries memories in more than light. It carries them in space-time. Our spacecraft passes through regions where ancient gravitational waves overlap. Signals from black hole collisions, neutron-star mergers, violent events from distant eras. Most are too weak to feel. But sensitive instruments could detect changes smaller than an atomic nucleus across large measurement systems. The cosmos is filled with invisible vibrations, a silent ocean of ancient catastrophes. As we continue backward through visible history, the galaxies become less organized. The grand spirals common in the modern universe become rarer. Many distant systems look small, irregular, clumpy, and unfinished. They are building themselves. Streams of gas feed them. Young stars ignite. Supernovae explode. Smaller galaxies combine into larger ones. The neat structures we recognize today emerge gradually from billions of years of interaction. A mature galaxy is not created in one moment. It grows. It absorbs neighbors. It loses gas. It changes shape. It develops a central bulge. Its spiral pattern strengthens or disappears. Its stars age. The universe we see nearby is the result of long development. The early cosmos shows the construction process still underway. Some ancient galaxies are compact, but produce stars at extraordinary rates. Others contain enormous amounts of dust created by early stellar generations. The existence of dust itself tells a story. The universe began mainly with hydrogen and helium, plus small traces of lighter elements. Carbon, oxygen, silicon, iron, and many other elements were created later inside stars. When stars died, they released those materials. Dust formed from the enriched gas. Finding dust in young galaxies means that stars had already lived and died there. Even an early galaxy can contain the remains of several stellar generations. Cosmic history moved quickly. Massive stars live fast. They can form, shine, create new elements, and explode within only millions of years. Compared with the age of the universe, their lives are brief. But those brief lives transform everything around them. They produce the material needed for rocky planets. They spread oxygen. They create iron. They enrich gas clouds. Without earlier stars, Earth could not exist. The atoms inside the human body required generations of stellar creation. The distant galaxies ahead are factories producing the chemistry of future worlds. At this stage in cosmic history, planets may already be forming around some stars, but their compositions could differ from those formed later. With fewer heavy elements available, rocky worlds may be less common. Gas giants may still form. Small primitive planets may exist. The universe is beginning to develop the diversity needed for complex environments. Whether life appeared this early remains unknown. Life may require planets, stable stars, chemistry, liquid environments, and long periods without catastrophic disruption. The early universe provided energy and material, but it also contained frequent explosions, active black holes, and dense interactions. Perhaps life began quickly in protected regions. Perhaps it needed billions of years of chemical preparation. Our journey cannot answer that directly. Light from distant galaxies is too weak to reveal microorganisms or oceans on individual worlds. The deeper we look, the larger the structures we can observe and the smaller the details we lose. A nearby planet can be studied as a world. A distant galaxy becomes only light. An early galaxy becomes a faint smudge. Information disappears with distance. This is one of the limits of astronomy. The universe may contain extraordinary details that no telescope can recover. a city on a planet billions of light-years away, would contribute almost nothing detectable to the total light of its galaxy. A civilization could rise, create art, question existence, and vanish without leaving any visible mark in our observations. We see the galaxy. We do not see the lives inside it. The past reaches us incomplete. As our spacecraft continues, the rate of star formation in the universe approaches its peak. Several billion years after the beginning, the cosmos produced new stars more rapidly than it does today. Gas flowed into galaxies, collisions compressed material, young stars illuminated dense clouds. The universe may have looked brighter in ultraviolet light, though dust absorbed and re-emitted much of that energy in infrared wavelengths. This era was filled with creation, not creation from nothing, but transformation. Gas becoming stars, stars becoming elements, elements becoming dust, dust becoming planets, gravity assembling structure at every scale. The universe was building complexity. Then, moving farther back, galaxies become increasingly rare and faint. We approach an era when the first large collections of stars were only beginning to appear. The darkness between them becomes more significant. The cosmic web exists, but many of its visible lights have not yet ignited. This is the period leading toward cosmic dawn. Before cosmic dawn, the universe passed through an age sometimes called the cosmic dark ages. The phrase does not mean nothing existed. Matter filled space. Dark matter structures were growing. Gas was gathering under gravity. Radiation remained from the early universe. But stars had not yet become common enough to illuminate the cosmos. There were no galaxies shining in the way we recognize today. No starlight spreading across the darkness. No heavy element-rich planets. The universe contained possibility before it contained visible complexity. The first stars changed that. They likely formed from clouds composed almost entirely of hydrogen and helium. Without heavier elements to help the gas cool efficiently, these early stars may have grown far more massive than most stars forming today. Some could have contained dozens or hundreds of times the mass of the Sun. They would have burned extremely hot and bright. Their lives would have been short, their endings violent. The first starlight may have been blue and powerful, a small number of stars emerging inside vast darkness. There were no earlier stars to enrich them, no planets with iron cores or carbon-rich chemistry nearby. Only primitive gas collapsing under gravity for the first time. These stars are sometimes called population the three stars. None has been directly confirmed as an individual object. They may have disappeared long ago. But their chemical fingerprints could survive in later stars and gas. Their explosions helped create the first significant quantities of heavy elements. They began the process that eventually produced planets, oceans, life, and observers. Imagine the first star igniting. There would be no one there to see it, no planet orbiting nearby with a night sky, no astronomer measuring its spectrum. But physically, the event would represent a major transition. The universe had become capable of producing a self-luminous object through gravitational collapse. Darkness was no longer complete. The star released ultraviolet radiation into surrounding hydrogen. That radiation changed the gas. It removed electrons from atoms, creating ionized regions around the star. More stars formed. Small galaxies appeared. The ionized bubbles expanded. Eventually, they began overlapping. This period is called reionization. To understand it, we must return to the gas filling the early universe. After the universe cooled enough for electrons and nuclei to combine into neutral atoms, much of space was filled with neutral hydrogen. This gas could absorb certain wavelengths of light. When the first stars and galaxies began shining, their energetic radiation ionized the surrounding hydrogen again. The universe slowly changed from mostly neutral gas to the largely ionized intergalactic medium observed today. Reionization did not happen everywhere at once. It likely began around the first luminous sources. Bubbles grew around young galaxies. Some regions changed early. Others remained neutral longer. The cosmos developed a patchwork appearance. Bright islands surrounded by differently behaving gas. Our spacecraft enters this era not as a place we could truly visit in the normal sense, but as a layer of time revealed by ancient light. The galaxies ahead are among the first. They are small, faint, difficult to detect. Their radiation is transforming the environment around them. They may merge rapidly. Many will eventually become parts of much larger galaxies. A tiny early system could contribute stars to the future Milky Way. The ancestors of our galaxy are scattered through this young cosmic web. The Milky Way did not exist yet in its modern form. Its future material occupied smaller dark matter halos and gas clouds. Those structures moved together over billions of years. They merged, collapsed, formed stars, developed a disk, absorbed other galaxies. Our home began as many separate pieces. Looking toward cosmic dawn is like looking at the childhood of every modern galaxy. But the farther back we travel, the harder observation becomes. The light has been stretched enormously. Galaxies are faint. Dust can hide star formation. The neutral gas between us and them absorbs important wavelengths. Astronomers must use large infrared telescopes and careful analysis to separate genuine ancient sources from nearer objects. A tiny red point can require months of study. Its distance must be estimated through its spectrum. Different filters reveal where its light disappears because of absorption and redshift. What looks like one faint dot can carry evidence from a time only a few 100 million years after the beginning. This is one of astronomy's greatest achievements. Humans standing on one planet can collect a handful of photons that traveled for most of cosmic history and use them to reconstruct the birth of galaxies. The photons may have crossed expanding space for more than 13 billion years. They passed through evolving intergalactic gas. They entered the Milky Way. They crossed our solar system. They struck a mirror. Then detectors converted them into data. A signal beginning before Earth existed becomes an image on a screen. The universe remembers itself through light, and astronomy learns to read the memory. Yet cosmic dawn is still not the oldest light we can see. Beyond the first stars lies a more ancient boundary. Before stars, before galaxies, before planets, before black holes formed through stellar collapse, the universe was filled with hot matter and radiation. At first, it was too hot for stable atoms. Electrons moved freely. Light scattered constantly from charged particles. The cosmos was opaque. A photon could not travel far without interacting. There was no clear view across space. If an observer could exist there, there would be no distant stars to see. Every direction would be filled with a hot, glowing plasma. As the universe expanded, it cooled. Eventually, temperatures fell enough for electrons to combine with atomic nuclei. Neutral atoms formed. Light no longer scattered as frequently. The universe became transparent. The photons released from that transition have been traveling ever since. Today, we detect them as the cosmic microwave background. This is the oldest light accessible through ordinary electromagnetic observation. It does not come from stars. It comes from the early universe itself. At the time of release, the radiation was much hotter and had much shorter wavelengths. Expansion stretched it into microwaves. Now it fills the entire sky. Every direction contains this ancient signal. The cosmic microwave background forms a kind of visible wall around our observations, not a physical shell surrounding Earth. A time boundary. We see it in every direction, because every line of sight eventually reaches a distance where the universe becomes opaque at earlier times. The source is not located at one permanent place. It represents the moment when light was freed to travel through the cooling cosmos. As time passes, the material that emitted the radiation continues moving and evolving. But we see its ancient state. If our spacecraft traveled billions of light years in one direction, the cosmic microwave background would still surround it. The observable boundary is centered on every observer. This is a crucial idea. Earth is not at the center of the universe simply because the oldest visible light forms a sphere around us. Any observer elsewhere would see their own sphere. The center belongs to perspective, not cosmic geography. Imagine standing in a thick fog. You can see a limited distance in every direction. The visible region surrounds you. Move elsewhere, and a new visible region surrounds your new position. The fog does not have you at its true center. Your visibility creates the appearance. The observable universe works differently in detail, but the analogy helps. Our cosmic horizon is defined by how far information has had time to reach us. Another civilization billions of light years away possesses a different observable universe. Much of it overlaps ours. Some regions visible to them are beyond our horizon. Some regions visible to us are beyond theirs. No single observer sees everything. Reality can be larger than the information available from one location. As our spacecraft approaches the cosmic microwave background in this imagined journey, the view becomes increasingly strange. There are fewer distinct objects. Galaxies disappear. Stars vanish. Individual light sources give way to a nearly uniform glow. But the glow is not perfectly smooth. Tiny temperature differences appear across it. Some regions are slightly warmer, others slightly cooler. The variations are extremely small, yet they became the seeds of everything that followed. Regions with slightly higher density attracted more matter. Gravity amplified the differences. Dark matter gathered. Gas fell inward. Stars formed. Galaxies appeared. Clusters and filaments developed. Every massive structure encountered during our journey grew from tiny early irregularities. The cosmic web is the enlarged result of subtle variations visible in the microwave background. Looking at that ancient radiation is like seeing the blueprint of the modern universe before the construction began. The pattern also contains information about the universe's composition and geometry. By measuring the size and distribution of temperature variations, scientists estimate how much ordinary matter exists, how much dark matter, how much energy behaves like dark energy, whether large-scale space is curved or nearly flat, how quickly the universe expanded at different times. The oldest accessible light becomes a report about the entire cosmos. But it also creates a limit. We cannot see ordinary light from earlier times because the universe was opaque. The cosmic microwave background blocks the electromagnetic view of the beginning. To study earlier moments, scientists must use other evidence: the abundance of light elements, gravitational waves, particle physics, the large-scale distribution of matter, the patterns in the microwave background itself. we can infer what happened before the oldest light without seeing it directly. This is similar to studying the center of Saturn or the inside of Earth. Observation does not always mean photography. Gravity, chemistry, motion, and surviving patterns can reveal hidden eras. Before the cosmic microwave background was released, the universe had already experienced hundreds of thousands of years of expansion and cooling. Before that, atomic nuclei formed during the first minutes. Hydrogen, helium, small traces of lithium. The temperatures were too high initially for nuclei to survive. As cooling continued, protons and neutrons combined. This process is called primordial nucleosynthesis. The resulting proportions of light elements match predictions remarkably well. The helium inside stars and planets carries evidence from the first minutes of existence. Some atoms around us are almost as old as the universe. The hydrogen in water may contain nuclei formed near the beginning. Matter from the earliest era eventually became clouds, stars, worlds, and living bodies. Our spacecraft is traveling toward the origin of material already present inside it. Earlier still, the universe was a hot mixture of particles and radiation. Conditions become increasingly difficult to reproduce or describe. At extremely early times, the known forces of nature may have behaved differently. Particles formed and interacted at enormous energies. Matter and antimatter were created. Most matter and antimatter annihilated one another. For reasons not fully understood, a slight excess of matter remained. That tiny imbalance made the present universe possible. If matter and antimatter had existed in perfectly equal amounts and behaved symmetrically, nearly everything might have disappeared into radiation. No galaxies, no stars, no planets, no observers. Something created an asymmetry, a difference so small in the early universe that it seems almost insignificant. Yet all visible matter may be the surviving result. The universe exists in its present form because of a slight imperfection. The deeper we travel into cosmic history, the more the large structures disappear and the fundamental questions emerge. Why is there more matter than antimatter? What is dark matter? What is dark energy? Why do the constants of nature have the values they do? Did the universe begin from a true singularity? Or does the singularity indicate that our equations are incomplete? These questions cannot be answered simply by traveling farther. The early universe is not waiting somewhere as a physical region we can enter today. It is a past condition. The cosmic microwave background is not a wall our spacecraft could reach and pass through. As we move, the horizon changes. The ancient emitting matter has evolved into stars and galaxies. We cannot fly into the past by crossing distance. This is where the imagined journey meets a profound limit. Looking far away allows us to see the past. Traveling to that location would take time. By the time we arrived, the region would be old. The young galaxy we observed would have changed for billions of years. The cosmic dawn we see is not physically preserved ahead of us. It survives only in light still reaching our position. Astronomy gives access to history without allowing us to enter it. The universe is an archive that cannot be walked backward. Our spacecraft can continue outward. But it can never arrive at the Big Bang by moving through space. The beginning occurred everywhere. Every region of today's universe was once part of that early hot state. Earth is not located far from the beginning. Earth is made from material that passed through it. The Big Bang was not an explosion from one point into surrounding emptiness. It was the expansion of space throughout the universe. Every large-scale location participates in the history. This means the beginning lies behind us in time, not ahead of us in one direction. There is no central crater, no outer shockwave moving through pre-existing darkness, no point where an explorer could find the birthplace of everything. The entire observable universe carries that origin. The cosmic microwave background surrounds us because the past surrounds every observer through delayed light. This transforms the meaning of our journey beyond the universe. We began by imagining movement outward. Earth to the planets to interstellar space, the Milky Way to other galaxies, the cosmic web to the observable horizon. But the final boundaries are not ordinary locations. They are limits of time, causality, and information. The edge of what we can see is not necessarily the edge of what exists. It is the edge of what has been able to communicate with us. Beyond that horizon, space may continue, galaxies may exist, structures may extend far beyond the observable region. Perhaps the universe is finite, but enormously larger. Perhaps it is infinite. Perhaps the same broad conditions continue without end. Perhaps regions beyond our horizon develop differently because of events in the earliest expansion. We cannot observe them directly. Light from those regions has not reached us. In some cases, because of accelerating expansion, it may never reach us. The horizon is not a distant wall waiting to be photographed. It is a boundary between what can influence us and what cannot yet, or may never, do so. Our spacecraft approaches this conceptual boundary while the universe continues expanding. The most distant visible galaxies fade behind stretched wavelengths. The microwave background becomes the oldest available light. Beyond it lies an earlier opaque era. Beyond our present horizon may lie additional space forever hidden from Earth. The journey has reached a place where sight becomes uncertainty. We know the observable universe is not necessarily everything. We know our horizon is shaped by the universe's age and expansion. We know space may extend beyond it. But knowledge becomes increasingly dependent on inference. The darkness beyond is not evidence of nothing. It is evidence of inaccessible information. And this may be more unsettling than a physical edge. A wall can be crossed. A border can be approached. An ocean can be navigated. But a causal horizon is different. It is not merely far away. The laws of space-time prevent its information from reaching us under current cosmic conditions. There may be worlds beyond it whose light will never enter our sky. Galaxies whose entire histories remain permanently unknown. Civilizations that can never discover us and can never be discovered by us. Not because either side failed to look, because expansion placed the regions outside one another's possible future. The universe may contain realities separated not by secrecy, but by physics. Our journey now pauses near the limit of observation. Behind us lies every structure we crossed. The Milky Way reduced to one galaxy among countless others. Clusters arranged into filaments, voids opening between them, ancient quasars shining from the age of rapid growth, young galaxies assembling, the first stars emerging, the microwave background glowing from the time atoms formed. Ahead lies the unknown beyond the observable horizon. There may be more universe, perhaps infinitely more. But no telescope can simply show it. No ordinary spacecraft can reach it. To continue, we must leave the language of familiar travel behind. The next stage will not be a journey through mapped space. It will be a journey through possibilities, through inflation, through cosmic curvature, through ideas of regions beyond our horizon, through the question of whether our universe is one complete reality or only one part of something larger. We have crossed the visible cosmos. Now we approach what visibility can never confirm directly, and beyond this point, the universe may become stranger than distance alone can explain. Beyond the observable universe, certainty gives way to possibility. We can calculate the age of the cosmos. We can measure the expansion of space. We can study the oldest light. We can map galaxies across billions of light years. But once we ask what exists beyond the cosmic horizon, observation can no longer provide a simple answer. The horizon does not mark the end of existence. It marks the end of what has had time to reach us. Beyond it may lie more galaxies, more stars, more planets, and perhaps more life. The universe could continue far beyond the region visible from Earth. It may be thousands, millions, or infinitely many times larger than the observable universe. Every direction could contain structures we will never see, not because they are hidden behind clouds or darkness, but because the distance between us expands too quickly for their light to arrive. This means there may be entire cosmic histories unfolding beyond our reach. Stars forming, galaxies merging, worlds evolving, civilizations rising beneath unfamiliar skies. They may look into space and ask the same questions we ask, yet neither side could ever know the other exists. Physics itself may keep us permanently separated, but perhaps the unseen universe is not simply more of the same. The earliest moments of cosmic expansion may have created regions with slightly different conditions. Some theories suggest that our observable universe could be one part of a much larger reality, divided into distant domains that can no longer communicate. Other ideas suggest that universes may form like separate bubbles inside a greater process. Each bubble could possess its own history, perhaps even slightly different physical properties. These ideas remain uncertain. They are possibilities built from mathematics and from attempts to explain the strange features of our universe. We do not know whether another universe exists. We do not know whether it could ever be visited, and we do not know whether the phrase outside the universe has a meaningful physical definition. If the universe includes all space and time, then asking what lies outside it may be like asking what lies north of the North Pole. The question assumes a direction that may not exist. Still, the human mind continues asking. We imagine walls, edges, and something beyond them because nearly everything in ordinary life has a boundary. A room has walls, a country has borders, a planet has a surface, a galaxy fades into intergalactic space. But the universe may not follow that pattern. It could be finite without possessing an edge. A traveler moving far enough in one direction might, in principle, return to where the journey began, just as someone traveling around Earth can return to the starting point without falling over an edge. Or space may continue forever. No boundary, no final wall, only more distance. If the universe is infinite, then our observable region is an unimaginably small window into endless reality. There could be galaxies beyond number, worlds beyond counting, events occurring at distances so large that they will never have any effect on us. Infinity is difficult to understand because human experience is built from limited things, limited years, limited landscapes, limited memories. Even the largest number we imagine remains finite. But an infinite universe would not simply be extremely large. It would have no final distance, no last galaxy, no point after which there is nothing more. Travel forever, and the journey never becomes complete. Perhaps that is the true meaning of going beyond the universe, not reaching another place, realizing that there may be no final place to reach. Every horizon becomes another beginning. Every discovery opens into a larger mystery, Earth once seemed like the whole world. Then it became one planet. The solar system once seemed like the full structure of creation. Then it became one star system among billions. The Milky Way became one galaxy among countless others. The observable universe became one region defined by light and time. And now, even that may be only a small part of reality. The farther knowledge expands, the smaller our position appears. But smallness does not mean meaninglessness. Humanity is physically tiny compared with the universe. Yet the universe, through us, has become capable of questioning itself. Atoms formed in ancient stars became planets. Chemistry became biology. Biology became awareness. Awareness looked into darkness and began reconstructing cosmic history. A mind existing for only a few decades can think about events billions of years old. A species living on one small world can measure galaxies far beyond its reach. We cannot cross the observable universe. We cannot visit the beginning of time. We may never know what exists beyond the horizon, but we can recognize the questions. And perhaps that is already extraordinary. Our imagined spacecraft has traveled beyond Earth, beyond the planets, beyond the Sun, beyond the Milky Way, and across the largest structures in the cosmos. But in reality, no spacecraft could complete this journey. The expansion of space, the speed of light, and the limits of time make it impossible. The journey belongs to imagination. Yet imagination is not meaningless. It allows us to connect scientific knowledge into a perspective no physical traveler could experience. It allows us to step outside familiar scales, to see Earth as a fragile point, to see galaxies as temporary structures, to see the observable universe as a horizon rather than a complete answer. And when we return from that imagined journey, Earth looks different. The sky is no longer merely dark. It is filled with ancient information. Every star becomes part of a larger history. Every galaxy becomes a distant island of time. The empty spaces between them become part of the architecture of reality. Even silence becomes meaningful because it may contain worlds whose messages can never reach us. We may never travel beyond the universe. But the question carries us beyond our ordinary way of thinking. It reminds us that reality does not need to fit inside human intuition. Space may be infinite. Time may have a beginning without an ordinary before. The observable universe may be surrounded by regions permanently inaccessible. Our cosmos may be unique, or it may be one among many. For now, the honest answer remains uncertainty, and uncertainty is not failure. It is the space where discovery begins. Every great scientific journey started with a boundary that seemed impossible to cross. The edge of the ocean, the top of the atmosphere, the far side of the moon, the outer planets, the ancient universe. Some boundaries became destinations, others became deeper questions. The cosmic horizon may belong to the second kind, a limit we may never physically cross, but one that teaches us how much remains beyond knowledge. So tonight, as we end this journey, imagine looking back, past the first stars, past the forming galaxies, past the cosmic web, past the Milky Way, past the Sun, back toward one small blue world moving quietly through space. That world is not the center of the universe. It is not the largest. It is not the oldest. But it is home. And for now, it is the only place we know where the universe has opened its eyes and wondered what lies beyond itself. Perhaps we will never find the final edge. Perhaps there is no final edge. Perhaps the journey beyond the universe has no destination. only a question continuing forever into the dark.